Today we are going to discuss inference. Inference is very important. Like I said at the beginning of this course, statistics can be classified into two groups: descriptive statistics and inferential statistics. We are done with first half of the semester, which means we completed everything about descriptive statistics. And we ended the descriptive statistics with two important concepts. We discussed the central limit theorem. After central limit theorem, we also discussed the confidence intervals. Now in inference, more applications of the central limit theorem. We can also use the confidence interval for all inferential statistics. That's the reason we have already discussed those two sections before working on inferential statistics. So what we mean by inferential statistics? Let's say, for example, I took a sample of, let's say, n equals 20. What is this? This is a sample size. I have collected my random variable on 20 subjects. And I calculated sample mean. The sample mean is given by x bar. Let's say my sample mean was equal to 48.7 for some random variable. Now, this is called a point estimate. We know that, right? We discussed that when we talk about the confidence intervals. Now, I just have one sample and I calculated one sample mean. And of course, I can calculate the sample standard deviation if necessary, which is given by S. And many other statistics can also be calculated, like the minimum and the maximum and the first quartile, second quartile, third quartile, median, and so on. Interquartile range and the lower limit and the upper limit. They're all descriptive statistics. We can calculate all of them. For the moment, let's forget about all the other things. I have calculated the sample mean. The sample mean is 48.7. Now, what does it say about the true population mean? We know the true population mean is given by mu. Okay, so this is the sample mean. The Greek letter mu stands for the true mean or the population mean. Now, this is an estimate of mu, that's for sure. But does it actually say that our mu is perhaps lesser than 50? Because my x bar is 48.7, which is lesser than 50. But is that really the case? Now, if I take another sample and calculate sample mean, will that sample mean also be lesser than 50? We don't know that. But we would like to answer this question. Is mu lesser than 50? Or on the other hand, since this 48.7 is almost equal to 50, and because I also know if I take another sample and calculate the sample mean, it will be different from 48.7. So can I just go ahead and conclude that the true population mean is just equal to 50 rather than 48.7. 48.7 is like, it's not a nice number, you know. We would like to go for a nice circular number like this. So these are two possible statements based on this value of sample mean. Another two possible statements may be, this is one combination of statements. And the other possible combination of statements is, well, mu equals 50 is a valid question, okay, because this x bar is very close to 50. So I would say, is mu equal to 50? It's a valid question. Or, on the other hand, I can also ask, is mu not equal to 50? Because this is 48.7, not 50. So this combination is also a valid combination of questions. In case, if my sample mean was, let's say, slightly larger than 50, x bar, the calculated x bar was equal to, let's say, 52.1. Now, in that case, one practical question is mu, the true mean, greater than 50? Or, on the other hand, I can say, is mu just equal to 50? Now, that's also a valid combination of questions. Valid combination with respect to this value of x bar. Now, with respect to this value of x bar, this combination is also making sense. But on the other hand, with respect to this value of x bar, this combination doesn't make sense because, clearly my sample mean is already larger than 50. Then why should I ask, can my true population mean be lesser than 50? That question doesn't make much sense. But if anybody wants, we can ask. Okay? So, these are three types of combinations of questions. If we know the answers, which out of these two statements in each combination is correct, we have some more concrete evidence about the true population mean. Say, for example, if I can conclude that my true population mean is equal to 50 based on my sample statistic, well, that's a very strong scientific conclusion. Or if I can conclude based on my sample statistics that the true population mean of the random variable of interest is significantly lesser than 50. That's also a strong scientific conclusion. Now, can we do that kind of conclusions? Now, how can we do that kind of scientific conclusions? That process is called inferential statistics. So today we are going to learn inferential statistics. All the theories of inferential statistics can be found in chapter number 17. Applications are discussed in chapter number 18 and 20. Well, what happened to chapter 19 then? Well, chapter 19 is a summary of what you discussed in chapters 17 and 18. So I'm going to skip chapter 19 and we will discuss chapters 17, 18 and 20. I'm planning to discuss all three chapters today within this single lecture. This will completely introduce you how to do inferential statistics for a single population mean mu. As usual, I have posted this lecture note on Canvas, so please go ahead and download that, and then you can watch this lecture and fill the blanks with me. Other point number 1, introduction to hypothesis testing. Inferential statistics is also called hypothesis testing. These are hypotheses. This is an example of possible combination of hypotheses. This is also an example of possible combination of hypotheses, and this is also an example for a possible combination of hypotheses. Now, which statement out of these two statements could be correct? Now, that test procedure is called hypothesis testing. In fact, if you carefully see these three combinations of hypotheses that I have written, actually they are called hypotheses, okay? I don't know whether this is true or whether that one is true. So these are just called hypotheses. These two are just called hypotheses, okay? Same here. Let's go to point number 1, introduction to hypothesis testing. Well, we can give a small definition for hypothesis testing this way. We're going to use sample statistics and test the values of the population parameters using those sample statistics. That's basically what we do. But in addition to that, sometimes some of the population parameters are also available to us, occasionally. So I would say more generally that hypothesis testing, which we can write under point number 1, hypothesis testing is the process of predicting unknown population parameters. Using the calculated sample statistics and any known parameter values. Any known parameters of the population. Now there can be so many parameters in a population, but today we are going to see just one parameter. That parameter is mu. True mean, or the population mean, mu. We are going to see if we can predict the values of mu using the sample statistics. What are the sample statistics? The sample statistics are basically x bar. And also the other statistics that will be used may be n, which is the sample size, and s, which is the sample standard deviation. And also we may use any known parameters of the population. Well, mu is definitely unknown. That's the reason we have to do hypothesis testing for mu. Now, in case if you know one parameter from the population, that parameter is possibly sigma. Okay, what is sigma? The lowercase sigma. Lowercase sigma stands for the true standard deviation. So not for all the cases, but sometimes sigma is available to us. When sigma is available to us, it actually has more information to predict mu. When sigma is not available for us, we will have to use the sample standard deviation. Let's go to point number 2. Hypothesis tests on population mean mu. Null hypothesis, which is given as h sub 0, and the alternative hypothesis, which is given as h sub 1. Now, what are those two statements? The alternative hypothesis can also be given as h sub a. Earlier we saw some equations like mu equals 50 and mu is larger than 50, or mu is lesser than 50, or mu is just not equal to 50, and so on. Now, to test those things, to decide which statement is correct, I'm going to need an equation. So how can I write down an equation? I need certain assumptions. In general, I will assume that the true population mean mu is equal to a value mu 0. Now this assumption will be tested. That's what we do under hypothesis testing. And then we see, test the assumption. Now this assumption is called the null hypothesis, h sub 0. And you write it like that and write two dots like this, and the statement is written as that. Now this mu 0 is a value given in the question. You will have to read carefully and figure out which value is mu 0. For the example that I discussed at the beginning of the lecture today, the mu 0 value is 50. And for another example, let's say I need to see, I have a collection of temperature readings today, and I need to see if the true mean temperature is equal to 70, or if it is different from 70, or if it is larger than 70, or if it is lesser than 70. Then that 70 is the mu 0 value. When you write mu is equal to that given value, it's called the assumption or the null hypothesis. Okay? And then we test if the assumption is true or false. If the assumption is true, then no problem. I can go ahead and accept that. But the problem is, if this assumption is false, then I must have an alternative to replace this assumption. So this assumption can be replaced in one of the three possible alternatives. So one alternative is, I could write mu is just not equal to mu 0. That's the most straightforward alternative. Another alternative could be mu is larger than mu 0. Or another possible alternative if this assumption is incorrect, is mu is lesser than mu 0. Now these alternatives, in case if our assumption is proved as false, we will go ahead and accept these alternatives. Okay, one of these three alternatives. We don't write all three alternatives for every single question. We write the assumption essentially, and with the assumption, we will write one of these three possible alternatives based on the instructions of the question. To determine which alternative should be selected, you have to read the question carefully. These alternatives are called alternative hypotheses. The alternative hypothesis has a symbol H sub 1, or you can write H sub A. So let me go ahead and use H sub 1. Okay. H sub 1 and then 2 dots. So this is one possible alternative hypothesis. And H sub 1 mu is not equal to mu 0. This is another possible alternative hypothesis. And H sub 1 mu is larger than mu 0. That's another possible alternative hypothesis. So I'll write down one more line. If the assumption or the null hypothesis is incorrect, then we say that our data support the alternative hypothesis. Okay? We don't know which alternative hypothesis. It should be one of these three alternative hypotheses. It will be clear later when we discuss examples, but for now I will just write if the null hypothesis is incorrect, we say that our data support the alternative hypothesis. That is, if your null hypothesis is incorrect. In case, if your null hypothesis is found to be correct, then we say our data will not support the alternative hypothesis. So I will write down that one also somewhere. If H0 is correct, then we say that the data do not support the alternative. This should make sense, right? Okay. Now these two statements should be written just like that when you interpret the test findings. They're going to be very important. But there's another piece of information that you should keep in mind. When you interpret, you will not use H sub 1. Okay? Instead, you must write your alternative hypothesis in words using the true mean and the random variable name given in the question, and whether this is lesser than a given value or whether it is not equal to a given value or whether it is greater than a given value. And also that given value should be specified. So it's very important to pay attention here. Whether your null hypothesis is incorrect or whether your null hypothesis is correct, the interpretation is written only about the alternative hypothesis. Okay? Which means interpretation should be only about the alternative hypothesis. Let's go to point number 3. Forms of hypothesis tests. We have left-sided tests, two-sided tests, and right-sided tests. Now what are those? We said for every single question, there will be a combination of hypotheses. One is the null hypothesis, the other one is the alternative hypothesis. So the null hypothesis is always, there's just one statement. The null hypothesis is always of the form mu is equal to mu 0. Now mu 0 is a given value in the question. Mu is the true mean of the random variable of interest. The alternative hypothesis, on the other hand, is one of these three forms. If your alternative hypothesis is like this, mu is larger than a given value, It's called the right-hand alternative. If your alternative is like this, that means if your mu is lesser than a given value mu0, then we call it a left-sided test. And if your alternative is just like this, mu is just not equal to that given value in the question, mu0. In that case, it could be larger than that given value or it could be smaller than that given value. To accommodate both scenarios, we say this is a two-sided alternative. Look for keywords. If you have to see if the true population mean is larger, greater, heavier, longer, that kind of words indicate that your alternative is a right-sided alternative. That means your alternative should be written as mu is larger than the given value mu0. Okay? And look for keywords again. If you see the keywords like lesser, lighter, shorter, that kind of words indicate that your alternative is a left-sided alternative. Mu is lesser than that given value. If the question is test, if the whatever the random variable name is different from a given value, it indicates that we have to write a two-sided alternative. The null hypothesis stays the same, just like this. Based on that, we have this classification: left-sided, two-sided, and right-sided tests. If you go to point number 4, there's an example given for a left-sided test, two-sided test, and right-sided test. Writing down the null and alternative hypothesis correctly after reading the question is extremely important. That's always the first step of a hypothesis test. Okay? And when you write down the null and alternative hypothesis, you will not write all of these. Read the question carefully and write down only one of these 3 that's appropriate for the question that you are answering. Now, in addition to that, there is one more thing that's required to do at this stage of writing down the null and alternative hypothesis. That is, you must define what's the meaning of mu. So mu is always the true mean of your random variable. Don't write true mean of the random variable. Instead, write true mean of, and then write down the name of the random variable. Let's go to point number 5. Tests on a population mean. You're going to see 2 different tests. One test is called the z-test. The other test is called the t-test. Just like in the confidence interval discussion, we do z-test if sigma is given. Sigma means the true standard deviation. If true standard deviation is explicitly given in the question, you must use the z-test. If sigma is not available, that means if you don't know the true standard deviation, in that case, you have to go for the sample standard deviation. With sample standard deviation, we do t-test. So let's write it down real quick. We do a z-test. We do a z-test if sigma is given in the question. And we do t-test. This is if sigma is unknown. That means we have to use S. Now what is sigma? What is S? Sigma is the true standard deviation. Okay? Sigma is the true standard deviation. Also called the population standard deviation. And S is the sample standard deviation. Now this understanding is extremely important. This is one place where there are many students making mistakes. We will see so many different inferential test procedures in the future. Already we are going to see two tests. One is z-test and the other one is t-test. Many students often forget when to use the correct test procedure. So let's be clear again. Select z-test if you are testing for a single population mean and sigma is given in the question. Select t-test. You are testing for a single population mean and if sigma is not given in the question. On the other hand, S or the sample standard deviation should either be given or the data set should be given to you so that you can calculate sample standard deviation. Okay? Alright, so let's keep that in mind and let's now move on to the next point. Point number 6, test procedures for z-test. We said there are 3 types of tests. We have left-sided tests and we have two-sided tests and we have right-sided tests. So we'll write down them real quick. A left-sided test can be written as the null hypothesis is mu is equal to mu 0 versus your alternative hypothesis is mu is lesser than mu 0. And a two-sided test can be written as null hypothesis is mu is equal to mu 0 and your alternative hypothesis is mu is not equal to mu 0. And a right-sided test can be written as your null hypothesis is mu is equal to mu 0, alternative hypothesis is mu is greater than mu 0. Alright, so these are the 3 forms of hypothesis we have. We have left-sided tests, we have two-sided tests, and we have right-sided tests. For all 3 tests, we have the same null hypothesis of the form mu is equal to mu 0. The direction of the test, whether it's a left-sided, two-sided, or right-sided, is determined by the form of the alternative hypothesis. For a left-sided test, we have the alternative hypothesis written as mu is lesser than mu 0. For a right-sided test, we have the alternative written as mu is greater than mu 0. For a two-sided test, we have the alternative hypothesis written as mu is not equal to mu 0. Okay, now for a given question, once again, remember, you will not write all 3. The given question will, one of these 3 only. It may be a left-sided test. If it is a left-sided test, you are not going to write two-sided and right-sided tests. Okay? And likewise, read the question carefully and select the appropriate test combination. Under point number 6, we are going to discuss the test procedures for z-test. That means I know the value of the true standard deviation sigma. For any form of hypothesis tests, there are 3 possible test procedures. The simplest of all 3 test procedures may be the confidence interval method. And there's another test procedure called the test statistic and critical value method. And the third test procedure is the p-value method. Okay? And we are going to see all 3 methods. Of course, the p-value method is actually even easier than the confidence interval method. However, at this point of time, we already know how to construct the confidence intervals. Now, because of that reason, the confidence interval method is discussed first, and it is actually very easy for us to understand. There are 3 types of confidence intervals as well. We had two-sided confidence intervals, we had lower confidence intervals, and we had upper confidence intervals. So what we do is, if you are testing a left-sided alternative, you construct a lower confidence interval. Okay? We often write it as 100 minus alpha %. So you do 100 minus alpha % lower confidence interval for this. For left-sided alternative. Now, how does a lower confidence interval look like? A lower confidence interval will go from negative infinity up to some fixed point. There is a fixed upper limit. Okay? And then, if you have a right-sided alternative, we're going to construct the upper confidence interval. You ought to know how to do that. Construct upper confidence interval. An upper confidence interval is of the form, there is a specific lower limit and the upper limit is positive infinity. Correct? And for two-sided alternative, what we do is we construct two-sided confidence interval. In a two-sided confidence interval, you have a fixed lower limit and a fixed upper limit. The test procedure is very simple beyond that point. We know the confidence intervals are constructed for the true population mean mu. Okay? The complete name of a confidence interval is actually a confidence interval for mean. Okay? So I would say the true mean is given by mu. So rather than just a lower confidence interval, I would say lower confidence interval for mu. And then we do it for two-sided alternative, we do a two-sided confidence interval for mu. For right-sided alternative, we do upper confidence interval for mu. Okay? Now, our assumption is written under the null hypothesis. The null hypothesis says the true mean mu is equal to mu 0. Mu 0 is a given value in the question. So how can I test if my assumption is true or false using the confidence interval? We know the confidence interval is constructed for mu. Our assumption says that the mu is equal to mu 0. So if my assumption is true, this mu 0 value should be found inside of this confidence interval. Okay? So if my assumption is correct, my confidence interval contains mu 0. In that case, we say our assumption is correct. If my mu 0 is not found inside the confidence interval, then we say our assumption, which says mu is equal to mu 0, is incorrect. Okay? I would write it like this. If mu 0 is found inside of the confidence interval, then we say we accept the null hypothesis. For example, let's say my mu 0 value is 50. Okay. Let's say we are working on a left-sided alternative. So the alternative is, I need to see if mu is lesser than 50. True mean is lesser than 50. I'm going to construct a lower confidence interval. Let's say my lower confidence interval is from negative infinity up to 60. Now that's an interval, negative infinity to 60. That interval contains 50, right? 50 is inside of that. Therefore, we say we accept the null hypothesis. The same way, I can say if mu 0 is not found inside of the confidence interval, I will say reject the null hypothesis. For example, if my mu 0 value is 50, let's say this time I'm doing a two-sided confidence interval, okay? Because I need to test a two-sided alternative. My mu 0 value is still equal to 50. Let's say my confidence interval is from 30 to 40. Now that interval, 30 to 40, does not contain 50. Okay? Therefore, we say our assumption or the null hypothesis is incorrect. So we say we reject our null hypothesis. Okay? So that's the technical procedure. Do you need another example for right-sided alternative? Let's say my mu0 is once again equal to 50. I'm testing a right-sided alternative. If my confidence interval goes from 70 to infinity, then 50 is not found inside of that. In that case also, I will reject my null hypothesis. Okay. For another example, if once again I'm testing the right-sided alternative with mu0 value is equal to 50, if my upper confidence interval is, let's say, from 40 to positive infinity, in that case, 50 is found inside of that. In that case, I will say I accept the null hypothesis. Now, interpretation is the next step. How do you do the interpretation? We said if our test accepts the null hypothesis, say for example, this is accepted. If it is accepted, that means our data do not support the alternative. Okay? This is accepted means the alternative is incorrect. In that case, we will say, we have to write this interpretation. We say, there is no evidence that the true mean of our random variable is different from the given value. We said no evidence because of this situation. So for example, I'm testing this combination, a left-sided alternative. And say I have my mu0 inside of the confidence interval constructed. In that case also, I will accept the null hypothesis. The null hypothesis is accepted means our data do not support the alternative. So once again, interpretation should be only about the alternative. So I would say our data do not support the fact that the true mean is lesser than the given value mu0. We can also specify the probability level, which is the same probability level used to construct the confidence interval. So if your confidence interval was a 95% confidence interval, interpretation should also contain that probability. I would say with 95% probability, our data do not support the fact that the true mean is lesser than the given value mu0 in this case. Look at another example. Let's say we have a confidence interval and we are testing this right-sided alternative, and my confidence interval did not contain the mu0 value. In that case, I will have to reject the null hypothesis. Rejecting the null hypothesis means the alternative is correct. That means our data support this statement. So we have to interpret it as that. Now because this is correct, we say we have statistical evidence to conclude that the true mean is larger than the given value mu0. Okay? We can also specify the probability level. So if you use a 95% confidence interval to obtain this conclusion, you can say with 95% probability, we conclude that the true mean is greater than the given value mu0. Okay? So to get that meaning, you can write in your own words, no matter how. Okay? But remember one thing, interpretation should only be about the fate of the alternative hypothesis. Testing is of course done for the null hypothesis, whether to accept H0 or reject H0. Interpretation is only about the alternative. Okay, so this is the test procedure using the confidence interval method. There are two more test procedures. The other test procedure is the test statistic and critical value method. For the test statistic and critical value method, I will simply use one of these three forms and derive an equation, and then we can argue the same way for the other two cases as well. So maybe the most complicated case is when you have a two-sided alternative. So I will derive the test statistic and explain you the procedure for two-sided alternative. So what you need for the test statistic and critical value method will be the central limit theorem, the most important theorem. The central limit theorem says you can have a random variable x with a mean of mu and a standard deviation of sigma. From any distribution, you take samples of size n, calculate sample means. Those calculated sample means will essentially follow a normal distribution, no matter what the distribution of original x. X bar will essentially follow a normal distribution with mean of mu and a variance of sigma squared over n. We will also need another part. This is from the discussion of the normal distribution before the first exam. Can you remember, we discussed something called the z-score. What is z-score? You can have a normal distribution, technically speaking, any normal distribution, and that any normal distribution can be mapped into the standard normal distribution. So for example, I have a normal distribution, let's say with a mean mu and a variance sigma squared. The standard normal distribution, what is it? The standard normal distribution is a z distribution. It will have normal 0, 1. Any point on this distribution, since it is a normal distribution, can be mapped onto the standard normal distribution. Okay? Let's say this is x. This will have a corresponding image on the z distribution. Let's say it's the z-score of x, zx. And I gave you this equation for zx. What was that equation? Zx is equal to whatever this x value minus its mean, which is mu, divided by its standard deviation, which is sigma. That gives you the z-score. Now what's the connection between this point and the z-score? The connection between those 2 points is, if you look at area to the right from x, that will be exactly equal to the area to the right from zx on the standard normal distribution. On the other hand, areas to the right are equal means areas to the left should also be equal to each other, because the total area of any distribution is equal to 1. Okay? So that's the connection. We are going to use this connection for x bar. We are going to map x bar into the standard normal distribution. But in the distribution of x bar, the variance is not just sigma squared. In the distribution of x bar, the variance is sigma squared over n. Okay? So I will have to modify this guy as sigma squared over n. That will affect this z-score calculation as well, because I need to divide it by standard deviation. So it will be divided by the square root of this variance, which is sigma over square root n. Sigma over square root n. That's my denominator. And there's another thing important. Now, this distribution is no longer the distribution of x. X can have technically any distribution. The central limit theorem gives us the distribution of x bar, the sample means. So this point is no longer just x. It is an x bar value, okay? The sample mean value, x bar. It is mapped into this point, zx bar. Let's say this point is called zx bar. So this x will also be changed to x bar. So we're going to use this guy to test our null and alternative hypothesis. If your null hypothesis is true, if H0 is true, now H0 says that mu is equal to mu0, right? So I can write this guy as mu0 if my assumption is true. But I have to test that. So instead of writing it as zx bar, I will write it as z test. Z test. I will write that numerator as x bar minus, the null hypothesis says this mu is equal to mu 0. X bar minus mu 0. The denominator stays the same, sigma over square root n. If your null hypothesis is true, what can you say about this statistic? I argue this way. If my null hypothesis is true, this statistic should be approximately equal to 0. Why? Because I know x bar is the sample mean. Sample mean is the point estimate for the true population mean mu. The null hypothesis says mu is equal to mu 0. If mu is equal to mu 0, the point estimate of mu, which is x bar, that should also be approximately equal to mu 0. Right? So if x bar is equal to mu 0, this numerator becomes almost 0. 0 divided by some number. That should be approximately equal to 0 if my null hypothesis is true. Now that's the foundation of the argument. We say if H0 is true, the Z test statistic, this is called test statistic, this is approximately equal to 0. It may not be exactly equal to 0 because x bar is just a point estimate, not the true value. So it will be approximately equal to 0 if our null hypothesis is true. That means here's the standard normal distribution, which is symmetric around 0. So how do you determine if our Z test statistic is approximately equal to 0? That's the next challenge. Let's say, for example, if your Z test statistic is equal to 1. Now, is it approximately equal to 0? Well, 1 is approximately equal to 0 maybe compared to 100. But on the other hand, compared to, let's say, 0.5, 1 may not be approximately equal to 0. So how do we determine that cutoff point? That's our next target. So what we have in hand is the calculated Z test statistic. Our target is to see if this calculated Z test statistic is approximately equal to 0 or not. To do that, we go back to the distribution of Z. Z distribution means the standard normal distribution. Let's see the standard normal distribution and Z test statistic. So here's the standard normal distribution. I'm going to draw it again. Standard normal distribution means I have Z and it's normal with mean of 0 and variance of 1. That's the standard normal distribution, which means our distribution is symmetric around 0. Now, if my Z test statistic is right on 0, then no problem that I will conclude that my null hypothesis is true. Well, if it is slightly positive, I'm still fine. Okay, slightly positive and okay, I can just ignore it and still assume it's almost equal to 0. If it is slightly negative, I will still ignore that and assume that my null hypothesis is true. So likewise, how far I can go away from 0? Now this is a two-sided test, so I can go for either side. Okay, so if it is positive and too large, I could say the null hypothesis is not valid. On the other hand, if it is negative and numerically too large, once again I can conclude this guy is not correct. So, practically speaking, I need two cutoff points. One positive cutoff point and another one which is a negative cutoff point. Beyond those 2 points, we can say the null hypothesis is no longer valid. As long as your calculated test statistic is within those 2 specified values, I can safely assume that the calculated test statistic is close to 0, which means I can safely assume that the null hypothesis holds true. How can we do that? So, the next task is to find those cutoff points. I know the total area is equal to 100% or 1 unit. How about 5%, maybe 10%? I'm going to keep about 5% or maybe about 10% evenly on these 2 tails of this distribution. That means I will allow maybe 95% of the area as close to 0. So, just like in a confidence interval, when you sacrifice some amount of probability from 100%, that amount can be called the error. And that error in the confidence interval was given as alpha, remember? I'm going to use that alpha again. I will keep half of alpha on the upper tail of the z distribution and another half of alpha on the left tail of this distribution. So this is half of alpha. This is also half of alpha. Of course, our preferred confidence level is 95%, which means alpha is 5%. If alpha is 5%, half of alpha should be 2.5%. Okay? So if half of alpha is 2.5%, what should be this point and what should be this point? Well, we already know those 2 points from the confidence interval calculations. They are called the critical values. How do you find those critical values? This is a standard normal distribution. Okay? So if your alpha equals 5%, half of alpha should be equal to 2.5%, which means it should be equal to 0.025. To find these 2 points, I have to go to distributions in TI-84CE plus calculator and then select what? It's not normal CDF because we are not finding probabilities. In this case, the shaded areas are given to us. The probabilities are given to us. What we need is this value and that value. Okay? Therefore, go to distributions and select number 3, inverse normal. And then you have to enter the area. Area in the inverse normal function is always area to the left. Okay? So if I enter this area as 0.025, I will get a negative answer as the critical value here. And I can just drop that negative symbol to obtain the positive critical value there. Okay? So the area should be equal to 0.025 because our alpha is 5% for this example. Almost for all cases in this class, take alpha as 5% unless otherwise stated. Area is 0.025 and then you have to define mu and sigma. So mu is equal to 0, sigma is equal to 1 because we are working with the standard normal distribution. And then you can select paste and hit enter. Let's go to your calculator. Here is our calculator. We need to go to distributions, second variables, that's where we have distributions, and then we can select number 3, inverse normal, hit enter. First, I have to enter the area, which we saw as 0.025. Mu is equal to 0, sigma is equal to 1. In this calculator, on the 4th line, I have the option to select whether the tail is left tail, right tail, or the center. That means if I entered the area in the first line
as the area on the left tail, or as the area in the middle, or as the area on the right tail. But most of the calculators don't have this option, unless, of course, you are using a TI-84 CE+. In all the earlier versions of the calculator, the area that you entered in the first step is taken always as left tail area. So if you enter 0.025 and mu is equal to 0, sigma is equal to 1, and select paste, you get a negative answer. But on this calculator, if I like, I can select right and hit enter. That should give me the right tail critical value, which is a positive answer. But I will go ahead and simply select left tail and hit enter, and then select paste and hit enter again, and hit enter again. So the critical value on the left tail is negative 1.96. That means the critical value on the right tail should be positive 1.96.
So we found the critical value. The critical value is 1.96. So this left endpoint is negative 1.96. The positive endpoint is positive 1.96. So as long as my calculated test statistic stays between these two values, or within this unshaded region of the standard normal distribution, I say that my null hypothesis is correct. Now these shaded areas are also called rejection regions. So this is a two-sided test. That's why I kept half of alpha on left tail and the other half alpha on the right tail. So from this point to infinity, which means from positive 1.96 to positive infinity, is one rejection region. The other rejection region is from negative infinity up to negative 1.96. So if your calculated z-test statistic is going to be in one of those intervals, we say we reject our null hypothesis. As simple as that. You can remember this equation for the calculation of the test statistic, but remembering is not required because your calculator has a very nice shortcut. But on the other hand, would you remember these critical values? Well, for the z distribution, if you are calculating z-test statistic, which means if you know sigma, these critical values are fixed. But remember one thing also, the critical values are fixed only for the z distribution. That means only for z-test. So if your calculated z-test statistic is going to be between negative 1.96 and positive 1.96, we say we accept the null hypothesis. In that case, our data do not support the alternative. So we write the conclusion that way. We have to always interpret the fate of the alternative hypothesis. So in this case, we will say our data do not support the fact that the true mean is different from the given value mu 0 with 95% probability, because we calculated these critical values taking alpha equals 5%. And in case if your calculated test statistic is, let's say for example, it was equal to 3.1. If it was equal to 3.1, the test statistic will be somewhere here, larger than 1.96. That means we will reject the null hypothesis. So if you reject the null hypothesis, that means we have to go ahead and accept the alternative. That means our data support the alternative. In that case, we will say we have statistical evidence, of course with 95% probability, to conclude that the true mean is different from the given value mu 0. That's how you can do the z-test statistic and critical value method for a two-sided test. Let's now see how to use the z-test statistic and critical value method for a right-sided alternative. Now, a right-sided alternative means I have my null hypothesis, like mu is equal to mu 0. The alternative hypothesis will be of the form mu is larger than mu 0. This is for the right-sided test. The calculation of the z-test statistic is exact same thing. Okay? x bar minus mu 0 all divided by sigma over square root n. And again, you don't have to remember this equation because your calculator has that function. In your calculator, of course, you will have to enter x bar and mu 0 value and sigma and n, and then it will calculate the test statistic by itself. Now, if my x0 is true, still this statement holds true. The test statistic should be approximately equal to 0. But on the other hand, if x0 is false, then eventually I will have to go ahead and accept the alternative. But the alternative says mu is larger than mu 0. Mu is larger than mu 0 means the estimate x bar should also be larger than mu 0. Now, if x bar is larger than mu 0, what can you say about x bar minus mu 0? X bar minus mu 0 should be positive, larger than 0. So, x bar minus mu 0, if that is positive, of course the bottom is positive by default always for the z-test statistic. So, if your numerator is positive, and if it is positive and too large, we say x0 is false. Well, if it is just slightly positive compared to 0, we will still ignore that. But if it is positive and too large compared to 0, in that case, I have to conclude that the null hypothesis is false. So, how large is too large compared to 0? That's what we have to see. Now here, once again, we go for the standard normal distribution. So here's the standard normal distribution again. That means our standard normal distribution, z distribution, has normal and 0, 1, and it's symmetric around 0. If my calculated z-test statistic is slightly positive, I will just say, okay, now this is close enough to 0. Somewhere here, maybe it's still close to 0, close to 0. Well, if it is somewhere there, right, far away, in the tail, then I have to reasonably conclude that my test statistic is significantly far away from 0. Just like earlier, in this case it's a single-sided test. This is a right-sided test, so keep complete alpha on the right tail. Complete alpha. So if it is 5%, okay, if alpha is 5%, what should be this critical value? Once again, we can find it from your calculator. You have to go to distributions and select number 3, inverse normal, and then you have to enter the area. Area of that function is always area to the left. Some newer versions of the calculator actually has the option to specify whether you entered a left tail area or a right tail area or a middle area. Okay, but most of the other calculators don't have that option, so I will tell you how to enter the left tail area. This is 5%, area to the left should be 95%. So area should be entered as 0.95. And then your mu is equal to 0 and sigma is equal to 1, select paste and then hit enter. Let's see that calculation.
Here's the calculator. Let's go to distributions, second, variables, and select number 3, inverse normal, and hit enter. Now in this calculator, on the 4th line, I can specify whether the area is left tail area, a center area, or a right tail area. So instead of entering area as 0.95, I have the option to enter 0.05 as the area, mu equals 0, sigma equals 1, and select tail as the right tail, and I can hit enter. Make sure to hit enter if you see this option of selecting the correct tail in your calculator. In case if your calculator does not show that 4th line of specifying the tail, in that case, your calculator assumes that the area that you entered is a left tail area. In such cases, you have to define the area as 0.95 since you are doing a right-sided test and we need that right critical value. So if I enter 0.95 in this calculator, I should select the tail as left and select and hit enter. And then we have to select paste and hit enter and hit enter again. The answer is 1.645.
We found that this value is 1.65. It's okay to write it as 1.645 as well, or you can write it as 1.65. So if your test statistic is even larger than 1.65, reject the null hypothesis. If it is in the unshaded region, which means if your test statistic is lesser than 1.65, you accept the null hypothesis. And occasionally students ask, what if the calculated z-test statistic is equal to 1.65? Well, I will still reject the null hypothesis even if it is equal. And in case, if you have a left-sided alternative, what will be the test procedure for z-test? For a left-sided test, I have mu is lesser than mu0. And just like the earlier case, since this is a left-sided test, I have to once again go back to the standard normal distribution. Z, normal, 0, 1. And this time I will keep complete alpha on the left tail because it's a left-sided test. Keep complete alpha on the left tail means if your alpha is 5%, what should be this critical value? Once again, you have to go to distributions, select inverse normal, area will be 0.05, mu equals 0, sigma equals 1, select paste and hit enter. And then we get this point is equal to negative 1.65, or you can write it as negative 1.645. Just like earlier, this is called, the shaded region is called the rejection region. So if your calculated test statistic is going to land on that rejection region, you reject your null hypothesis. If the calculated test statistic is in the white interval, we accept the null hypothesis. And interpretation will be accordingly decided for alternative. Now say for example that my calculated test statistic for this case is negative 2.3. In that case, the test statistic is somewhere here, 2.3. Therefore, I have to reject my null hypothesis because this shaded area is called the rejection region. That's all about the test statistic and critical value method for z-test. And there's another test procedure which is the p-value. So let's now see what we mean by the p-value. Now the p-value method can also be explained for those three forms of the hypothesis tests. But on the other hand, the p-value method has just one guideline. No matter whether your test is left-sided, two-sided, or right-sided, there's just one guideline for the p-value. We can have left-sided, two-sided, and right-sided tests. And no matter what, your null hypothesis is always of the form mu is equal to mu0. And then I need the alternative hypothesis, and based on the alternative hypothesis, the direction of the test is determined. Okay? So if it's a left-sided test, the alternative should be of the form mu is lesser than mu0. And if it's a right-sided test, the alternative should be of the form mu is larger than mu0. Two-sided means the alternative should be of the form mu is not equal to mu0. All right, we saw it so many times. To understand the p-value method, we will once again look at the calculated test statistic and the critical value method for a second, and then we will derive just one statement, simple statement for the p-value. For a left-sided test, what we did was, now here's my z distribution. Since this is a left-sided test, I kept complete alpha on the left tail. And I said this is the rejection region. For a right-sided test, what we did was we kept complete alpha on the right tail. And we said this is the rejection region. For a two-sided test, what we did was we kept half of alpha on each tail. The shaded intervals were called the rejection regions. So we calculated the test statistic, and if the test statistic is going to land on the shaded intervals, we said we reject the null hypothesis. So if you look at the right-sided alternative, if my test statistic is somewhere here, I reject the null hypothesis. For a left-sided test, if my test statistic is somewhere here, I reject my null hypothesis. On the other hand, for a two-sided test, I can have my test statistic somewhere here, or I can have my test statistic somewhere there. I'm going to reject the null hypothesis in each case. Now, we are going to define something called the p-value. The p-value is defined this way. For a right-sided test, the p-value is the area to the right from the test statistic. So if your test statistic is here, area to the right means this shaded area. That's called the p-value. For a left-sided test, the p-value is defined as area to the left from the test statistic. So here's the test statistic, and this is my area to the left. This is the p-value. For a two-sided test, the p-value is defined slightly differently. Well, for a two-sided test, you can have your test statistic, and it could be positive or it could be negative. It cannot be both positive and negative at the same time, right? Because we have just one x bar and one specific mu zero value. So once you take the difference for the numerator of that z test statistic, you will have one answer only. That could be positive, that could be negative. But on the other hand, we are going to consider both signs to calculate the p-value. Let's say for a two-sided alternative, your calculated z test statistic is positive. Say for example, positive 2.3. Then you will also consider negative 2.3. We need positive test statistic as well as the negative test statistic. The p-value for a two-sided test is defined this way. Area to the right from the positive test statistic plus the area to the left from the negative test statistic. If this is my positive test statistic, this will be the negative test statistic. And they should be symmetric because the z distribution is symmetric around 0. So area to the right from positive test statistic means this. Area to the left from negative test statistic means this. So on each tail, the shaded area should be half of p because of the symmetry. Okay. Now, all three cases have some specific characteristic to reject the null hypothesis. Which one is larger? P-value or alpha for this case? Alpha is larger, p-value is smaller. In this situation, I reject my null hypothesis. Okay? So this point is the test statistic. Look at this left-sided test. This point was the test statistic. Now which one is larger? Alpha is larger, p is smaller. We reject the null hypothesis in this situation. Look at this one. This is half of p, this is half of p, and here's half of alpha and here's half of alpha. The total p is this area plus that area, and that total p should be smaller compared to total alpha, which is the summation of this shaded red area plus this shaded red area. Okay? So, no matter whether your test is left-sided two-sided or right-sided, if your p-value is lesser than alpha, you reject your null hypothesis. Let me write down that guideline. It's very important. If p-value is lesser than alpha, which is 0.05 always, if your p-value is lesser than 0.05, then you reject H0. So no matter whether this H0 comes from a left-sided test, two-sided test, or a right-sided test. And in your calculator, you have a function for calculation of the z-test statistic. It will calculate the z-test statistic as well as the p-value. So we can kind of blindly use that p-value and come to the conclusions. But on the other hand, you also have to know how to find the p-value when the test statistic is given to you. It might sound somewhat intimidating to some students, but don't worry. If you practice a few more examples, we will do that. After that, the p-value calculation will not be a big deal. So that's that, and we have completed the discussion of all three test procedures for z-test. Then if you go to point number 7, it's actually testing procedure when sigma is not available. Those testing procedures are similar, but I'll come back to point number 7. But before that, let's go to point number 8. There's a full-length example given under point number 8. Point number 8 is the place where we begin chapters 18 and 20. In chapter 18, we discuss inference in practice. And in chapter 18, all the examples are for the case where sigma is given. Okay? And then for chapter 20, we will discuss the cases where sigma is not given, which is a complete different test procedure. Please go ahead and read problem number 8 and see if you can answer the question yourself. And then you can come back and watch the video for my solution. Well, it is the very first question of this kind that we are going to discuss. So even if you find it like a little bit difficult to understand, that's completely natural. So just go ahead and read the question. I will help you understand how to answer that question. Okay, good. Let's read that question. Point number 8, a bearing used in automotive application is supposed to have a nominal inside diameter of 1.5 inches. A random sample of 25 bearings is selected and the average inside diameter of those bearings is found to be 1.4975 inches. The bearing diameter is normally distributed with sigma equals 0.01 inches. You need to test if the true mean diameter is different from 1.5 inches. The term different, I have underlined that in this lecture note. That's very important. That's the keyword which indicates the direction of the test. Because I'm using the term different from 1.5, it says it's a two-sided test. The mu0 value is 1.5. Part A, write down the null and the alternative hypothesis to be tested. Clearly define the terms used. I have to first define mu. Okay? So I'm going to let mu be the true mean inside diameter of the type of bearings given. Then I need to write down the null and alternative hypothesis. So if you read carefully, the last sentence of that first paragraph says, you need to test if the true mean diameter is different from 1.5 inches. So the null hypothesis and alternative hypothesis are clear. The alternative hypothesis, I need to see if the true mean diameter is different from 1.5. The null hypothesis, once you have this number, can be very easily written. It's always mu is equal to 1.5. That's all I need for part A. And then if you go for part B, what's the type of statistical test procedure that should be used to test the hypothesis? Explain. Well, this is the very first type of hypothesis, so you only know z-test. So of course, this is an example from the z-test. Of course, we discussed 3 test procedures, but all 3 test procedures are called in general z-test because sigma is given. And that's what I expect as the answer for part B. The reason I ask part B is this. In the future, you're going to see so many test procedures. So it's very natural sometimes that some students tend to forget which test has to be used under which given scenario. Okay? So always we practice this procedure. Part B, what's the test? And you have to explain why do you use that specific test. So if you read this question carefully, we can see that sigma, or the true standard deviation of the diameter, is given. Sigma is equal to 0.01. Therefore, we say, part B, I need to go for z-test. The reason is sigma is given. Selecting the correct test procedure for a given scenario is extremely important. If you select an incorrect test, all the calculations beyond that point will be totally incorrect. And then part C, construct a 95% confidence interval. Test the hypothesis using the confidence interval. Interpret the test result clearly. Now this is a two-sided test. Okay? So I can straight away construct a 95% two-sided confidence interval. And that 95% two-sided confidence interval should be a Z confidence interval. So I will need a 95% two-sided Z confidence interval. We already know how to calculate the Z confidence intervals, correct? Using your calculator. And also we can use the equation if you want to. I gave you the equations during our discussion of confidence intervals. Well, I prefer to use the calculator. Let's go to the calculator.
Here's the calculator, and you can also see the first 3 parts of point number 8. And we are going to construct a confidence interval. The confidence interval is a Z confidence interval because sigma is given to us. To construct the two-sided 95% Z confidence interval, we will go to Stat, select Tests, and then you have to scroll down until you see Z confidence interval. Select number 7, Z confidence interval. Hit Enter. Of course, for this question, we do not have a data set. Therefore, the input method should be statistics. Select stats as the input method and hit Enter. And then we can define sigma x bar in and the confidence level. Sigma is equal to 0.01. X bar, the sample mean, is equal to 1.4975. N, it's a random sample of 25 bearings. Therefore, N equals 25. As we saw earlier, we are constructing a 95% two-sided confidence interval. Therefore, the confidence level remains as 0.95. Select, calculate, and then hit Enter. Make sure that you hit Enter only one time. The 95% Z confidence interval for the true mean bearing diameter is from 1.4936 to 1.5014.
So the confidence interval we get is from 1.4936 to 1.5014. That's the 95% two-sided Z confidence interval. So what's the test procedure now? After constructing the confidence interval, I have to see if the mu0 value, which is 1.5, is inside of this confidence interval. Of course, the lower limit is lesser than 1.5 and the upper limit is larger than 1.5. Therefore, 1.5 is found inside of this confidence interval. That means mu equals 1.5 makes sense. Okay? Because this is the confidence interval for mu and it contains 1.5. Since 1.5 is inside the confidence interval, we say we accept the null hypothesis. Accept the null hypothesis. Accepting the null hypothesis means our data do not support the alternative. And interpretation should be written only as that. Interpretation is only about the alternative. Our data do not support the fact that the true mean inside diameter is different from 1.5. We should also specify the probability level. So we will write it this way. We have no statistical evidence. No, because of this, no statistical evidence with 95% probability. 95% because this confidence interval is 95% confidence interval. No evidence with 95% probability to conclude that the true mean inside diameter which is mu in words, true mean inside diameter, is different from 1.5, which is our H1, okay, is different from .5 inches. Remember, we said no statistical evidence because our data did not support this statement. And I wrote down this statement as it is. True mean inside diameter is different from 1.5. Okay, that's the complete interpretation of this test. Let's now go to part D. Part D says, test the hypothesis using the test statistic and critical value method. You must clearly indicate the test statistic and the critical values used. Take alpha equals 5%. Do you get the same answer as part C? If different, interpret the test findings. I need the Z test statistic for part D. The Z test statistic is given by this equation. Z test equals x bar minus mu 0 over sigma over square root n. Correct? X bar value is the sample mean given in the question, which is equal to 1.4975. Mu 0 value is 1.5. Sigma is given in the question as 0.01. And n is the sample size, which is 25. So we can use this equation if you really want to, but there's a shortcut in your calculator. Rather than just calculating all that, we can use that function. I'll show it to you in a minute, but before that, what should be the critical value? With the test statistic, I should also provide the critical value. Okay? So the critical value is, I need to go for the standard normal distribution, and it's a two-sided alternative. Two-sided alternative means I should keep half of alpha on the right tail and the other half alpha on the left tail. And I have two critical values. We take alpha equals 5%, so half of alpha is 2.5%. And then these two values will be 1.96 and negative 1.96 respectively. Now I need the test statistic and see if it lands on one of these shaded regions. Well, of course, based on our previous answer, it should not land on the rejection regions because we accepted the null hypothesis based on the confidence interval. So based on the test statistic method as well, I should accept the null hypothesis, which means my calculated test statistic should not land on these shaded intervals. Okay, let's go to the calculator and calculate the Z test statistic.
Here's the calculator. Now we have to calculate the Z test statistic. For that, we have to go to Stat, select tests, select number 1, z-test, hit enter. Input method. We do not have a dataset. For this question, we have statistics given. Therefore, select stat as the input method and hit enter. Then you have to enter the mu0 value. The mu0 value is equal to 1.5, which is the value written on the right-hand side of the null and the alternative hypothesis. Sigma is equal to 0.01. Then we have to enter x bar, which is 1.4975. Then we have to enter n, which is the sample size. N is equal to 25. Now those values are imported automatically from the previous calculation of the confidence interval. In the next line, you have to define the alternative hypothesis. This time it is a two-sided test. Therefore, select mu is not equal to mu0 and make sure to hit enter. Selecting the correct alternative hypothesis in that step is extremely important when you go for answering part E of the question. In part E of the question, you have to use the p-value. P-value will be incorrect if you do not select the correct alternative in this step. The next line is color, which you can skip, and then select calculate and hit enter. Always check the first line of the calculator output. The first line should indicate your alternative hypothesis. The first line of this output says mu is not equal to 1.5, which is the alternative hypothesis. Therefore, you can go ahead and count on the rest of the output. The second line indicates that z equals negative 1.25. That is the calculated z-test statistic. The p-value is shown in the third line. The p-value is equal to 0.2113 approximately.
Z-test statistic is equal to negative 1.25. So negative 1.25 is somewhere here. So it's not in the rejection region. Therefore, once again, we accept the null hypothesis, which means this is correct and we get the same conclusion. You don't have to interpret again. You can simply say you have the same answer or same interpretation. And then we can go for part E. Part E says, what's the p-value of the test? Test the hypothesis using the p-value. Take alpha equals 5%. Do you get the same answer as parts C and D? If different, interpret the test findings. Of course, all these methods should give you the same answer. So the p-value, this is a two-sided test. How do you calculate the p-value? The calculated test statistic is negative 1.25. And we define the p-value for a two-sided test as area to the left from the negative test statistic plus the area to the right from the positive test statistic. So area to the left from negative 1.25 is this, and area to the right from positive 1.25 is the other half. Well, of course, I have the p-value in the z-test output of your calculator, but also I just wanted to show you how to calculate the p-value using the z-test statistic in case if you have a question like that. So we can, of course, straight away use that output, but in case if you would like to calculate manually using the calculated z-test statistic, this is how you do that. I have to go to the z distribution. That means I have to go to distributions and select normal CDF. And then this is a z distribution, which means z is normally distributed with mean of 0 and variance of 1. And then you can find just one of these two areas. By symmetry, they are equal. This is half of p, this is also half of p. And so just find one of them and multiply your answer by 2. That should be the complete p-value. Then I can define my lower limit as 1.25. The upper limit is something large, positive 100 million. And mu is 0, sigma is 1. And then select paste and hit enter. The third line, which is 0.2113. Of course, for part E, all I need is the p-value. P-value is equal to 0.2113. So what's the test procedure for p-value? We said, if your p-value is lesser than alpha, reject your null hypothesis. Now in this case, it is not lesser than alpha. In fact, it is larger than alpha. Therefore, we say accept the null hypothesis. And that means we get the same interpretation as two earlier cases. So you don't have to interpret again, simply write down the interpretation is the same. That's it about question number 8. So let's go to problem number 9. It's a similar question. The alternative is slightly different. Please go ahead and read the question and see if you can answer. I think you can answer it now. Problem number 9. A new design for the braking system on a certain type of car has been proposed. For the current system, the true average braking distance at 40 miles per hour under specified conditions is known to be 120 feet. It's proposed that the new design will be implemented only if sample data strongly indicates a reduction in true average braking distance for the new design. Assume that sigma equals 10. A sample of n equals 36 observations indicated that average braking distance was x bar equals 115.2 feet. Part A, write down the null and the alternative hypothesis to be tested. Clearly define the terms used. This is about the true average braking distance. So we will define mu as that. Problem number 9, part A. I will let mu be the true average braking distance of that certain type of car traveling at 40 miles per hour under specified conditions. That's a complete definition of mu, but this should suffice for our purposes. And then I have to see if there's a reduction. Okay. Reduction compared to 120 feet. The standard length is 120 feet. So the null hypothesis can be written as mu is equal to 120. The alternative should be mu is, if there is a reduction, it indicates we are testing for left-sided alternative. Mu is lesser than 120. If the new design suggests that mu is lesser than 120, that new design will be implemented. And then if you go for part B, what's the type of statistical test procedure that should be used to test the hypothesis? Explain. Once again, it's about one population mean, and if you read the question carefully, you can see that sigma is given. Sigma is given as 10. So I would say it's z-test. The reason is sigma is given. And then part C, construct a 95% confidence interval. Test the hypothesis using the confidence interval. Interpret the test result clearly. Now, this is a left-sided test, which means I will need a 95% lower confidence interval, not a two-sided confidence interval. Okay? So how would you construct a 95% lower confidence interval? What's the first step? In the discussion of confidence intervals, under one-sided confidence intervals, we saw that our calculator doesn't have the option to construct one-sided confidence intervals. So we tricked that. What we did was we constructed a two-sided confidence interval. Right? We constructed 100 minus 2 alpha% two-sided confidence interval. Then, for this case, we can replace the lower limit with negative infinity. So 1 alpha will be gone. So from 100 minus 2 alpha, when you put 1 alpha back, you get 100 minus alpha% confidence interval. That's what we did. So in this case, alpha equals 5%, 95% confidence interval means alpha equals 5%. 100 minus 2 alpha should be therefore 90%. This is very clear. Okay. So first we do 90% two-sided z confidence interval for mu. let's go to your calculator.
Here's the calculator. We have to construct a Z confidence interval. There is no data set given. Therefore, there is no data entry step. So we can straight away construct the Z confidence interval. We have to go to Stat, select Tests, and then you select number 7, Z interval. Hit Enter. Input method is Statistics. Select Stats and hit Enter. And then you can define sigma, x bar, and n. Sigma is given in this question as 10. X bar is equal to 115.2. N is equal to 36. The confidence level. As we saw earlier, we need a 95% lower confidence interval, but the calculator will not give us a lower confidence interval. Therefore, using the calculator, we are going to construct a 90% two-sided Z confidence interval. Therefore, the confidence level should be 0.9. You can enter it as 0.90 as well. So the calculator will now give us a 90% two-sided Z confidence interval. For that confidence interval, we can simply replace the lower limit with -infinity to obtain a 95% lower confidence interval. Select, calculate, and then hit Enter. Make sure that you hit Enter only one time. Here is the 90% two-sided Z confidence interval. The lower limit is 112.46. The upper limit is 117.94.
I got 112.46 as the lower limit, and the upper limit is 117.94. But this is not the confidence interval that I need. This is 90% two-sided. What I need is 95% lower confidence interval. So from this one, I can obtain 95% lower confidence interval. I simply have to replace this lower limit with -infinity. And the upper limit stays the same. That's my 95% lower Z confidence interval for the true mean breaking distance. Now what I have to do is to see if 120 is inside of this confidence interval. Well, the confidence interval is from -infinity up to 117.94. Clearly, 120 is not inside. Okay? 120 is not inside. That means I have to reject the null hypothesis. We say reject the null hypothesis. Now, reject null hypothesis is only an intermediate step. The final solution should be given in terms of alternative hypothesis. Since this was rejected, the alternative should be correct. Okay. And we interpret H1. Our data supported this statement. So we say, interpretation, I will write down somewhere here. We have statistical evidence with 95% probability to conclude that the true average braking distance is lesser than 120 feet. We have statistical evidence with 95% probability to conclude that the true average braking distance is lesser than 120 feet. Okay. I said we have, because our data supported this statement, and I said 95% probability because I used a 95% confidence interval, and to conclude that the true average braking distance, which is mu inwards and is lesser than 120. That is, mu is lesser than 1. That's the alternative hypothesis written in words. Let's go to part D. Test the hypothesis using the test statistic and critical value method. Take alpha equals 5%. And if you get the same answer, we don't have to interpret again. And we can simply write down that it is the same interpretation. For part D, so I will not write down the equation for the calculation of Z test statistic. You already know what that equation is. And anyways, we are not going to use that equation. We will simply enter those values into your calculator. But what we need for this one is the critical value. Okay? So it's a left-sided alternative. Left-sided alternative means is the Z distribution. I'm going to keep the complete alpha on the left tail. And what is this critical value? Well, that should be negative 1.65. In case if you cannot remember that, you can find it. This is 0.05, and this distribution is the standard normal distribution, Z normal 0, 1. So you can go to distributions, select number 3 inverse normal, and enter area as 0.05, mu equals 0, sigma equals 1, then you should get negative 1.65 as your critical value. And then what we need is the calculated Z test statistic. And we can see that the confidence interval method rejected our null hypothesis. So we should get the same thing using the test statistic critical value method as well. Your test statistic should be in the shaded interval. That means it should be lesser than negative 1.65. Let's see if that's the case. Let's go to your calculator.
Here's the calculator again. This time we need a Z test statistic, and we already constructed the Z confidence interval for this question. And we still have the confidence interval also on the screen. I'll go ahead and clear that. And because we already constructed the confidence interval, you will see some of these values that we previously entered are still available as the values of X bar, sigma, and N, and so on, for the calculation of the Z test statistic as well. So to calculate the Z test statistic, I'll go to Stat and select Tests and select number 1, Z test. Hit Enter. Input method is still Statistics. Select Stats and hit Enter. Then we have to define mu0 value. What is this mu0 value? Mu0 value is the value written on the right-hand side of the hypothesis statements. We wrote down the null hypothesis as mu is equal to 120 for this question. That 120 is the mu0 value for this question. Therefore, enter 120 as the mu0 value. Sigma is equal to 10, X bar is equal to 115.2, N is equal to 36. Now, those values are automatically imported from the previous calculation of the confidence interval. The next line is extremely important. The next line indicates the alternative hypothesis. You have to specify whether it is a two-sided test, a left-sided test, or a right-sided test. Here we are doing a left-sided test. So it is of the form mu is lesser than mu0. Select lesser than mu0, which is the one in the middle of that line, and then make sure to hit Enter. If you do not hit Enter, the correct alternative will not be selected. Of course, for the calculation of the test statistic alone, this step is not critically important. Irrespective of whether your test is two-sided, left-sided, or right-sided, the test statistic will be properly calculated. But if you go for the next part of this question, you will need the p-value. The p-value will be affected by the direction of the test. There's one p-value for the two-sided test, there's one p-value for the right-sided test, and there's another p-value for the left-sided test. Therefore, because of the p-value, this step is extremely important. Please pay special attention at this step when you define the alternative hypothesis. I need to emphasize this because in the past, so many students did not select the correct alternative at this step. Even if they selected the correct alternative, I guess some of them forgot to press Enter. When you do not press Enter, the correct alternative will not be permanently selected. Simply skip color select calculate, and then hit enter. Now here is the z-test output. The first line is extremely important. That's where you can see whether you entered the correct alternative hypothesis. Look at the first line. The first line says mu is lesser than 120. The first line indicates the alternative hypothesis. So this is the place where you can check whether you entered the correct alternative hypothesis. If your alternative hypothesis is correct, then you can count on rest of the output of this calculator. The second line indicates the test statistic. For this question, the test statistic is negative 2.88. That's what we need to answer this part of the question. When you read the next part of the question, you will see that you will also need the p-value. The p-value for this question is equal to 0.001988.
Calculated test statistic was negative 2.88. Therefore, it's clearly in the rejection region. So I would say reject the null hypothesis. That means you get the same answer as earlier, same interpretation as well. And yes, it's enough to write just as same interpretation. It's understood. We have already written down the interpretation explicitly in part C. Then we can go for part E. What's the p-value of the test? Test the hypothesis using the p-value. So what's the p-value? It was in the calculator's output, part E. The p-value is 0.001988 something, so I will write it as 0.002. And clearly, this value is lesser than 0.05. And we said if your p-value is lesser than alpha, we reject the null hypothesis. Okay? So we reject the null hypothesis. That means we get the same interpretation again. That's the answer for part E. If you want to find the p-value manually, how would you find it? So it's a left-sided test. P-value will be the area to the left from the test statistic. So this area is the p-value. So how do you find it? You have to go to distributions, select normal CDF. The lower limit will be something like negative 100 million. The upper limit is negative 2.88. Mu is equal to 0. Sigma is equal to 1. Select, paste, and hit enter. You should get the same p-value as the p-value given in your calculator's output. Of course, yes, you can find the p-value just by reading the calculator's output. But occasionally in the multiple choice section of your exams, I give you the calculated test statistic, and also I will tell you whether it's a left-sided test or a right-sided test or a two-sided test, and I might ask you to calculate the p-value without providing any further information. So in such cases, please make sure that you also know how to manually calculate the p-value. So we'll do more examples in the future, so that part will become clear in the future. So that's all about the z-test. And if you go to point number 10, that question doesn't have sigma given. So what test procedure can be used when sigma is not given to us? We're going to see that next. So to discuss the test procedures when sigma is not given, let's go back to point number 7. Testing procedures for t-test. We do t-test if sigma is not given. Please remember that. Okay, it's very important. Point number 7. T-test. This is when sigma is unknown. That means S should be given, or the data set should be given so that you can calculate S. What is S? S is the sample standard deviation. Okay. That means we have to use S, the sample standard deviation. Let's see how to do this calculation. Once again, you can have those 3 forms of tests. You can have left-sided, two-sided, or right-sided tests, which means I can have tests of the form null hypothesis is mu is equal to mu 0. The alternative is mu is lesser than mu 0. That is the left-sided test. Or you can have a two-sided test. That means I can have my null hypothesis is mu is equal to mu 0. And the alternative hypothesis is mu is not equal to mu 0. And we can have right-sided tests. For a right-sided test, the null hypothesis is once again mu is equal to mu 0. The alternative is of the form mu is larger than mu 0. And we have those three procedures under t-test as well. The three test procedures are the confidence interval method, that's the first one. The second one is the test statistic and critical value method. And the third one is the p-value method. For the confidence interval method, we are going to construct t confidence intervals. For a left-sided test, construct 100 minus alpha percent lower t confidence interval. Lower t confidence interval means the lower limit will be negative infinity and there is a certain fixed upper limit. And for a right-sided test, you construct a 100 minus alpha percent upper t confidence interval. For upper t confidence interval, the upper limit is positive infinity. There is a fixed lower limit. And for two-sided alternatives, construct 100 minus alpha percent two-sided t confidence interval. It will have a fixed lower limit and it will have a fixed upper limit. So the test procedure is just like earlier. See if mu 0 is inside of the confidence interval constructed. If it is inside the confidence interval, we accept the null hypothesis. If mu 0 is not inside the confidence interval, we reject the null hypothesis. Just like earlier, interpretation should be only about the fate of the alternative hypothesis. So if the null hypothesis is accepted, the conclusion should be of the form, we have no statistical evidence to support the alternative. If the null hypothesis was rejected, that means our data support the alternative, and we write it that way. We have statistical evidence to conclude that the alternative holds true. That interpretation should be written in the context of the problem given. You can't just write alternative holds true or alternative doesn't hold true. Okay? So you have to write what is mu, you have to use a random variable name, and you have to indicate the value that you compare, that mu, and also indicate the probability level, which is often 95% for all the calculations of this class. That's it about the confidence interval method. And then we can go for the test statistic and critical value method. We have these three forms of tests, left-sided, two-sided, and right-sided tests. And there's just one equation for the calculation of the test statistic. Just like in the Z test statistic calculation, we have a similar equation for T test statistic. In the Z test statistic, the numerator was x bar minus mu 0. And for the T test statistic is also, we have the same numerator. So it will be x bar minus mu 0. In the Z test statistic, the denominator was sigma over square root n. Now in this case, we don't know sigma. So we are going to use the sample standard deviation instead. So this equation will be written as S over square root n. That's all. That's the calculation of the test statistic. Well, you don't have to remember this equation because your calculator has the t-test statistic function, which can be used straight away. But just for the completion of the lecture, I gave you the equation of the test statistic. And then we have to use the critical values. Now these critical values are very important. Why do we go for t-distribution? Now in this part, we don't know sigma. That means there are more unknowns in that distribution of the random variable. With the z-test, we at least knew sigma. Here, we at least don't know sigma. Therefore, we have to allow some more variability. To allow more variability, that means to reach the same level of accuracy, I have to allow more variability. To allow more variability, I have to use t-distribution because the t-distribution has thicker tail probabilities compared to the z-distribution. That's the reason we select the t-distribution for this purpose. And as we saw earlier, the t-distribution depends on the degrees of freedom. That means the t-distribution is not just one distribution. It's a collection of distributions. When the degrees of freedom is equal to 2, you have one distribution. When degrees of freedom is equal to 3, you have another one. 4, you have another one. 5, you have another one. 6, you have another one, and so on. How do you calculate the degrees of freedom? Degrees of freedom is equal to n minus 1, where the sample size is equal to n. Say, for example, I'm going to use a sample of 20. What should be the degrees of freedom? 20 minus 1, which is 19. Okay? So t-distribution should always be written with its corresponding degrees of freedom. So if it is a t19 distribution, you can write it as that, t19. Okay? In general, I will write t sub df. So remember that df stands for degrees of freedom, which is equal to n minus 1. Okay? df, or the degrees of freedom, is equal to n minus 1 for the t distribution. In order to find the critical values, if it is a left-sided test, you keep complete alpha on the left tail. Okay? And often this alpha is equal to 5%. And if it is a right-sided test, you keep complete alpha on the right tail. And if it is a two-sided test, you keep half of alpha on the right tail, the other half of alpha on the left tail. Then you get two critical values. The shaded regions are called the rejection regions. So our task first is to find these critical values. And then we can identify the rejection regions, and then you can go for the calculator function for the calculation of the t-test statistic. If that test statistic is going to land on one of these shaded regions, we are going to say that the null hypothesis is rejected. So we'll do a quick example of finding the critical values. Okay? Let's first find a t critical value for a left-sided alternative. Let's say I'm going to use a sample of size 20. And I need this left critical value. So degrees of freedom should be equal to 19. That means the distribution of interest is t19. Okay? So I have to first go to distributions and select inverse t. And then I should enter the area. Now this area, let's say alpha equals 5%. Always enter area to the left in that function. Okay? Remember to enter the area to the left. The shaded area is equal to 5%. And that's an area to the left. So I can enter area as 0.05. And then you have to define the degrees of freedom. Degrees of freedom is equal to 19. And then select paste, and then hit enter. You're going to get the critical value for the left-sided test. Let's go to your calculator.
Here's the calculator. We have to go to distributions, second variables. That's where we have distributions, and select number 4, inverse t. Hit enter. Area is area to the left. We said area is 0.05 for that left-sided example. Degrees of freedom is equal to 19. Select paste and then hit enter. And you have to hit enter again. The left-sided t critical value for this example is negative 1.729. Remember, the critical values for the t distribution are not fixed. They always will depend on the degrees of freedom.
We got negative 1.729. You can see that the rejection region is from negative infinity up to negative 1.729. Say, for example, your calculated t-test statistic is equal to negative 3.2, which is clearly in the rejection region. In that case, you will reject your null hypothesis. If your calculated t-test statistic is, let's say, negative 0.8, in that case, it is in the white region, which means we accept the null hypothesis. We'll do another example for the two-sided alternative. Let's say this time I'm going to use a sample of 15. Alpha is still 5%. I need these critical values. How can I find them? Degrees of freedom will be equal to 14. And alpha is 5%, which means half of alpha should be equal to 2.5%. And therefore, I can go to distributions again, select inverse t, which is number 4, and if you enter area, what should be the area? Area should be 0.025. Remember, in that function, area means always area to the left. If you enter 0.025, what you get is this critical value, which is a negative value. And you can simply drop that negative and obtain the other critical value, which is the positive value, because this is symmetric around 0. T distribution is also, just like Z distribution, it is symmetric around 0. Let's go to your calculator and see what that value is.
Let's go to distributions, second variables. That's where we have distributions, and then we have to select number 4, inverse t. Hit enter. Area, we're going to enter area as half of alpha, which is 0.025. Now that value should give us a left-sided critical value, which is a negative value. What if I straight away wanted the positive t critical value? In that case, what should be the area that I should enter? We know the total area of a distribution is equal to 1 unit. So if I enter 1 minus 0.025, which is equal to 0.975, you should get the positive value of the critical value that you're going to see on this screen. But I'm going to leave it as 0.025. Therefore, we will get a negative answer. Degrees of freedom for this example is equal to 14. And we will select paste and hit enter again. We have two t critical values. The value on the left tail is equal to negative 2.1448. The value on the right tail should be positive 2.1448.
We got negative 2.145. By symmetry, the other value should be positive 2.145. If your calculated test statistic is in between these two values, we accept the null hypothesis. If it is in the shaded intervals, we reject the null hypothesis. All right, we will also find the critical value for one example from right-sided alternative. Let's say I'm going to use a sample of 10, n equals 10 this time. Alpha stays as 5%. That means my degrees of freedom should be equal to 9 this time. If I go to your calculator, select distributions, number 4, inverse t, what should be entered as the area? Be careful. I have to enter area to the left in that calculator to get this positive answer. If you just enter 0.05, it will be the corresponding negative answer. You will have to drop that negative symbol to get this positive answer. Okay. So if I need to enter the complete area to the left, I can get that positive answer. What should be this area to the left? Alpha is 5%. So the area to the left should be 95%, which is 0.95. Okay. All right, we'll do it that way. Let's go to our calculator again. We'll go to distributions, second, variables, and select number 4, inverse t, hit enter. The area, we will enter area as 0.95, degrees of freedom is equal to 9, and select base and hit enter again. The required critical value is 1.833. We got 1.833. So from positive 1.833 to positive infinity is the rejection region. So if my test statistic is 4.2, for example, I can reject the null hypothesis because it is in the rejection region. That's how you can do the test statistic and critical value method. And then we have the p-value method. Once again, we have that same just one guideline, irrespective of the form of the test, whether it's left-sided, two-sided, or right-sided. So the guideline is, if your p-value is lesser than alpha, reject the null hypothesis. That means, if your p-value is lesser than 0.05, reject your null hypothesis. If your p-value is greater than alpha, we accept the null hypothesis. Interpretation should be in the context of the alternative hypothesis. We only interpret the alternative hypothesis. So how do you calculate the p-value? Of course, if you run the t-test procedure in your calculator, it will give you the p-value as well. But as students of Introstat, we should also know how to calculate p-value manually if the degrees of freedom and the calculated test statistic, and whether the test is left-sided, two-sided, or right-sided is given. Okay? So let's see. If I have a right-sided test, the p-value should be, I have to first calculate the test statistic. Let's say my test statistic is somewhere here. The p-value is area to the right from that test statistic. You can find it by accessing TCDF. I have to go to distributions, select TCDF, and then enter the value of the calculated test statistic as the lower limit. Upper limit is something positive and large. Degrees of freedom should be entered thereafter. And then select paste, hit enter, you get the p-value. And for a left-sided test, how do you calculate the p-value? P-value will be area to the left from the calculated test statistic. So if your calculated test statistic is somewhere here, the p-value will be area to the left from that point of this t-distribution. If you need to find that using your calculator, you will have to go to distributions again, select TCDF. The lower limit will be something like negative 100,000. Upper limit will be the calculated t-test statistic, and then you have to enter the degrees of freedom. And that's it. For a two-sided test, you're going to need both positive and negative values of the test statistic. If your calculated test statistic is, let's say, positive 3.1, it will be somewhere here. Then you will also need negative 3.1. The p-value is defined as area to the right from the positive test statistic plus area to the left from the negative test statistic. Of course, you can simplify in one of those two areas and multiply your answer by 2 in order to obtain the complete p-value. Let's do an example. Go to point number 10 and read it. Of course, you can answer parts A and B. For the other parts, I will help you. Problem 10. To investigate water quality Columbus dispatched 2 water samples at 20 Ohio State Parks viewing areas. Those samples were taken to laboratories and tested for fecal coliform, which are E. coli bacteria found in human and animal feces. An unsafe level of fecal coliform means that there is a higher chance that disease-causing bacteria are present and more risk that a swimmer will become ill. Ohio considers it unsafe if a 100 milliliter sample of water contains more than 400 coliform bacteria. Here are the fecal coliform levels of 20 samples. The dataset is given. Part A, write down the null and alternative hypothesis to be tested. Clearly define the terms used. Well, in this lecture note, I have underlined more than 400, more than. That's the keyword. So it indicates that we are doing a right-sided alternative. Okay? So for part A, I will define mu first. I will let mu be the true mean coliform bacteria level. And I had to see if it is more than 400. The null hypothesis can be written as H0 is mu is equal to 400. Alternative hypothesis can be written as H1, which is mu is greater than 400. Part B, what's the type of statistical test procedure that should be used to test the hypothesis? Explain. So if you read this question carefully, there's no place where sigma is given, and we still have to do inference on one population mean, and sigma is not given, so our choice is t-test. So we'll write it as that. Part B, t-test, because sigma is not given. And part C, construct a 95% confidence interval. Test the hypothesis using the confidence interval. Interpret the test result clearly. Well, this is the right-sided test. So what I need is a 95% upper confidence interval. So what's the first step? First step is I have to construct a 90% two-sided P confidence interval for mu. And then we can replace the upper limit with positive infinity in order to obtain the 95% upper T confidence interval for mu. Let's first do the 90% two-sided using your calculator.
We need to construct a 95% confidence interval using the given data. The first step is to enter the complete dataset into your calculator. To enter the dataset, I have to go to Stat, select Edit, select number 1, Edit, and then hit Enter. You can enter all the given data points into the list L1. To save time, I have already entered all the given data points into the list L1. Once you finish entering all the data points, we can construct the T confidence interval. For that, you have to go to Stat, select Tests, and this time we are going to construct a T confidence interval, which is given under point number 8. Select number 8 T interval and hit Enter. Input method. We do not have the statistics in this example. We only have the raw data set. Therefore, the input method should be selected as data. Hit Enter. The list. You have to define the list label where you entered all the data points. We entered our data set into the list L1. Therefore, the default list shown on this screen is correct. In case if you entered them into a different list, please make sure to define the correct list. If you do not see L1 or the list where you entered your data, you have to define it using second and corresponding key. L1 can be defined as second and 1. L2 can be defined as second and 2, and so on. There is no frequency list in this given data set. Each individual data point is given rather than a frequency table. Of course, in this class, you will never get any frequency table. I will always give you single data points. So for all the future calculations as well, frequency will always be equal to 1. In the next line, you must define the confidence level. What we need is a 95% upper T confidence interval. The calculator will only give you two-sided T confidence intervals. So we construct 90% two-sided confidence interval using the calculator. Therefore, the confidence level should be defined as 0.90. Then select calculate and then hit enter. Now on the screen, you can see the 90% two-sided T confidence interval. The lower limit is 773.63. The upper limit is 1598.9. By replacing the upper limit with positive infinity, you can obtain the 95% upper T confidence interval.
All right, so the 9% two-sided T confidence interval for mu is 773.63 is the lower limit, and the upper limit is 1598.9. Now from that, we can obtain the 95% upper T confidence interval. 95% upper T confidence interval for mu should be, the upper limit will be replaced with positive infinity and the lower limit stays the same, 773.63. To test the hypothesis, I have to see if the mu zero value, which is 400 for this case, is inside of this confidence interval. The lower limit is 700 something, and 400 is clearly not inside of this confidence interval. Therefore, I must reject the null hypothesis. Rejecting the null hypothesis means, I will also write it down, reject null hypothesis means our data support the alternative hypothesis. And I must interpret that statement. So how would you interpret? We say we have statistical evidence with 95% probability to conclude that the water is unsafe, or you can write it this way, that the true mean coliform levels true mean coliform level is more than 400. I said we have statistical evidence because our data supported this statement. 95% probability because 95% is the probability used in the confidence interval. The true mean coliform level is mu in words and is more than 400 is the alternative hypothesis written in words. Okay. Part D, I had to test the hypothesis using the test statistic and the critical value method. Now this has 20 data points. This means the distribution I should use is T19. For part D, I need T19 distribution. And it's a right-sided test, so I'm going to keep complete alpha on the right tail, which is 0.05, and then I have to find this critical value. How do you find that critical value? We have to go to your calculator.
We need a T critical value. For that, I have to go to distributions first. To access the distributions, I have to press second and variables. Now, what's the distribution I should select? This time, I have to find a T critical value, which means I know the probability. It's a right-tailed T critical value. We keep complete alpha on the right tail. That means area to the left should be equal to 1 minus alpha. When alpha is equal to 5%, 1 minus alpha is equal to 95%, which means 0.95. That means I have the probability. And I have to do the inverse calculation in order to obtain the critical value. That means I have to go for inverse t. Select number 4, inverse t, hit enter. Area is equal to 0.95. Degrees of freedom. We had 20 data points. Therefore, 20 minus 1, 19 is degrees of freedom. Select paste and then hit enter and hit enter again. The t critical value required for that calculation is 1.729.
Critical value is 1.729. Now we need to calculate the test statistic. We of course know that the test statistic should be in the shaded region because we should get the same conclusion as part C. Alright, let's go to your calculator and calculate the t-test statistic.
To calculate the test statistic, you have to first enter the given dataset. We already entered the dataset earlier in the calculation of the confidence interval, so we can straight away go ahead and calculate the test statistic. For the calculation of the t-test statistic for the data, I have to go to Stat, select Tests, and select number 2, t-test. Hit enter. Input method is data. Select data and hit enter. Mu0 value, which is the value written on the right-hand side of the two statements of the hypothesis. The mu0 value is equal to 400. The list. This is a list where you entered the data. We entered the data into the list L1. Frequency is always equal to 1. The next line is important for the calculation of the p-value. This is a right-sided test, which means it is a test of the form mu is greater than mu0. Select greater than mu0 and hit enter. Remember, if you do not hit enter, the correct alternative test will not be selected. Selecting the correct alternative test is required for your p-value to be correct, even though it does not affect the calculated test statistic. Skip color, select calculate, and then hit enter. Always check the first line of the calculator output. The first line indicates the alternative hypothesis. We are testing an alternative hypothesis of mu is greater than 400. That's what we see in the first line of this output. Therefore, we can go ahead and use the rest of the output without any doubt. The second line indicates the calculated t-test statistic. The t-test statistic is equal to 3.2948. The third line indicates the p-value for the test. The p-value is 0.0019.
The calculated test statistic is 3.29. So 3.29 is somewhere here. Therefore, we reject the null hypothesis. That means we get the same interpretation as earlier. Now, what should be the p-value? The p-value is, because this is a right-sided test, I have shared area to the right from the test statistic. We need the p-value for part E. So if I need to find the p-value using the distribution and the test statistic, we can do that. I have to go to distributions, select TCDF, enter 3.29 as the lower limit. Upper limit is something positive and large, such as 100 million. Degrees of freedom is 19. And that's all, and you get the p-value. But also, we can simply read the p-value from the calculator's output. The p-value is 0.0019, which is clearly lesser than alpha. When the p-value is lesser than alpha, or 0.05, we reject the null hypothesis. That means we get the same interpretation again. So you don't have to write it again for part E. All right, that's one complete example from the t-test. Of course, for the exams also, you can expect these kinds of questions, full-length questions with 5 parts. Always, the part A will be to write down the null and alternative hypothesis, and part B to identify the test with reason why did you select that specific test, and part C confidence interval method, part D, test statistic critical value method, and part E always is the p-value method. Okay? So if you can remember this order, and when you are familiar with this order after trying a couple of questions, it'll be really easy to navigate the rest of this class. Okay, let's go to point number 11. Please read the complete question and see if you can answer. You should be able to answer comfortably. Point number 11, the desired percentage of silicon dioxide in a certain type of aluminous cement is 5.5. 16 independently obtained samples are analyzed. The sample statistics are the sample mean x bar equals 5.25. The sample standard deviation S equals 0.3. We need to test if the true mean silicon dioxide percentage significantly differs from 5.5. Pay attention to the keyword differs. That indicates we're going to test a two-sided alternative. And the mu0 value is 5.5. Part A, write down the null and the alternative hypothesis to be tested, clearly define the terms used. So I will let mu be the true mean silicon dioxide level. And I have to see if mu is different from 5.5, which means my null hypothesis should be mu is equal to 5.5 versus the alternative hypothesis should be mu is not equal to 5.5. This indicates we have a two-sided test. And then part B, what's the type of statistical test procedure we have to select and explain. Of course, sigma is not given in that question. The sample standard deviation S is given. That means I have to go for t-test. T-test. The reason sigma is not given. And then part C, construct a 95% confidence interval, test the hypothesis using the confidence interval, interpret the test result clearly. Of course, this is a two-sided test, so we can straight away construct a 95% two-sided confidence interval, T confidence interval for mu. 95% two-sided T confidence interval for mu. We have to go to the calculator.
Is the calculator. I have to construct a T confidence interval. There's no data set given. We have all the statistics. So there's no data entry step. We can straight away go to stat, select tests, and then scroll down until you see T interval. Select number 8, T interval, and hit enter. Input method. Input method is statistics. Select stats and hit enter. Now you can define all the given statistics. X bar is given as 5.25. Sx stands for the sample standard deviation, which is equal to 0.3. N, which is the sample size, they took 16 independent samples. Therefore, N equals 16. Confidence level. We are doing a two-sided test, and we need a two-sided 95% confidence interval. Therefore, we define the confidence level as 0.95. Select, calculate, and then hit enter. The 95% two-sided T confidence interval is from 5.0901 to 5.4099.
The 95% two-sided T confidence interval for mu is 5.0901 is the lower limit. The upper limit is 5.4099. All right. Now I have to see if mu0 value, which is 5.5, is inside of this confidence interval. Is it inside it? No, 5.5 is outside of this interval. It is outside. That means I have to reject my null hypothesis. That means our data support this alternative. I would say reject null hypothesis, and then I need to interpret this in the context of the problem given. Interpretation is always only about the alternative hypothesis. Our data supported that the true mean silicon dioxide level is different from 5.5. We have 95% probability to conclude that. So we will say we have statistical evidence with 95% probability to conclude that the true mean silicon dioxide level is different from 5.5. That's it. And then we go for part D. Test the hypothesis using the test statistic and critical value method. Now this is from a data set of 16 data points. Therefore, the degrees of freedom should be equal to 15. So for part B, the distribution we have to use is T15. And it's a two-sided test. Two-sided test means I have to keep half of alpha on the left tail and the other half of alpha on the right tail. Alpha is 0.05, so half of alpha should be 0.025. 0.025. And then we need to find these two critical values first. Let's go to your calculator and find them. We need to go to distributions, second, variables, that's where we have distributions, and we have to select number 4, inverse t. Select number 4 inverse t and hit enter, and the area is 0.025. Area means area to the left. When you enter the area as 0.025, you will get the critical value on the left tail, which is a negative value. In order to obtain the other critical value on the right tail, all you have to do is to drop the negative symbol. Degrees of freedom is equal to 15. Select paste and then hit enter and hit enter again. The left tail critical value is negative 2.131. So the critical value is negative 2.13 for the left tail, and therefore by symmetry, the right tail critical value should be positive 2.13. And now I need to calculate the test statistic. Let's go to the calculator again. To calculate the t-test statistic, I have to go to Stat, select Tests, select number 2 t-test, hit enter, and the input method is Statistics. Select Stats and hit enter. The mu0 value. We are comparing the true mean silicon dioxide percentage with 5.5. Therefore, mu0 value is equal to 5.5. X bar is equal to 5.25. Sx is equal to 0.3. N is equal to 16. Those values are automatically imported from the previous calculation of the confidence interval. Next, we have to define the alternative hypothesis. The alternative hypothesis is two-sided. Select mu is not equal to mu0 and hit enter. Skip color and select calculate and then hit enter. Always check the first line of this output. The first line should indicate your alternative hypothesis. Our alternative hypothesis is mu is not equal to 5.5. That's what we have in the first line of this output. Therefore, we can go ahead and use rest of the output without any problem. The calculated t-test statistic is negative 3.33. The p-value of the test is 0.0045. The test statistic is negative 3.33, which will be somewhere here. So clearly it's in the rejection region. Therefore, we say we reject the null hypothesis. And just like earlier, we get the same conclusion, okay? Same interpretation. If I need to find the p-value, I can simply read the calculator's output, and if I need to use the calculated test statistic and the distribution, I can find area to the left from negative 3.33 and then multiply that by 2 for the complete p-value, because this is a two-sided test. Or in other words, you can find area to the right from positive 3.33 and add those two half p-values, and that should give you the complete p-value. But for this question, we don't have to do all that, and we can simply read the p-value from the calculator's output. For part E, the p-value is 0.0045, which is clearly lesser than alpha, which is 0.05. And we said when the p-value is lesser than alpha, we reject the null hypothesis. That means we get the same interpretation again. And it's enough to write that for part E. But please make sure that you don't just write the same interpretation just everywhere. Make sure that all the required parts are shown, okay? I need this p-value for part E. And for part D, I need these critical values and I need the test statistic. Without all these pieces, if you just write same conclusion, you will not get points. All right, so that's that example, and I think now you have a solid foundation on the z-test as well as the t-test. And there are a few additional pieces that I would like to still add. They are given on page number 8 under points number 12, 13 and 14. Let's go to those 3 points and discuss these things real quick. Point number 12, type 1 error alpha. Of course, we discussed alpha when we talked about the confidence intervals. That was the first time we defined alpha. Alpha was defined as error. I think I used the term type 1 error as well, but I didn't explain why it is called type 1 error at that point. The reason why alpha is called type 1 error is because there's another possible error in statistics when we perform hypothesis tests. The very first one is alpha, which is therefore called type 1 error. We will see why it is called type 1 error, and we will also see the other possible error, which is called type 2 error. We've seen 3 types of hypothesis: left-sided, two-sided, and right-sided. I will just pick one of those 3 forms just for the simplicity of the discussion to revisit the definition of alpha. Okay? Let's say, for example, I have to do the null hypothesis is always mu equals mu 0. The alternative, let's say mu is greater than mu 0. So this could be a z distribution if sigma is given and t distribution if sigma is not given. So I don't know what this distribution is. Let's say this is one of those distributions. And because this is a right-sided test, I must keep complete alpha on the right tail. And this value right here is the critical value. We should read this critical value first. And then we calculate the test statistic. If the calculated test statistic lands on this rejection region, what we do is we reject our null hypothesis. And we conclude that our data support the alternative hypothesis. Well, all these conclusions are reached using just a sample of data points. But in reality, what if the true mean is actually equal to mu 0? Well, in reality, mu is equal to mu 0, but my sample says otherwise. So this statement was denied from my sample, which is an error, isn't it? It is an error, but what's the probability of error? Well, I will reject my null hypothesis only if my test statistic is going to be on this area. And that area is just equal to alpha. This is the very first error that we allow. Therefore, this is called type 1 error. So I will define it this way. Type 1 error, this is written under point number 12. alpha, type 1 error. This is the probability of rejecting the null hypothesis when the null hypothesis is actually true. Okay. Probability of rejecting the null hypothesis which is h sub 0 when h0 is true. Let's go to point number 13. There's another possible error that we might commit when we do hypothesis tests. Can you tell me another way that we can make an error? Earlier we said probability of rejecting the null hypothesis when the null hypothesis is true is an error. The other possible error is probability of not rejecting the null hypothesis when the null hypothesis is false. Okay? And that error is defined as type 2 error beta. Probability of not rejecting h0 when h0 is false. Type 1 error is always taken as 5% for all the calculations of this class. And then how about type 2 error? Well, the type 2 error can be calculated. I will set up a separate video explaining how to calculate type 2 error, but learning how to calculate type 2 error is not a required part for the calculations of intro stat students of this class. So you can safely skip the calculation part of type 2 error for this class. But on the other hand, I might give you type 2 error for a different calculation, which is given under point number 14. Power of a statistical test. We said beta is the probability of not rejecting the null hypothesis when the null hypothesis is false. So this scenario, null hypothesis is false, stands. What if I calculate 1 minus beta? What will that be? 1 minus beta should be the probability of rejecting the null hypothesis when the null hypothesis is false, which is a correct decision. That's what we want to do. Therefore, that quantity, 1 minus beta, is defined as the power of the statistical test. And you have to remember this one. So in the exams, I might give you that the probability of type 2 error is, for example, 30%. Find the power of the statistical test. If the question is that, you have to subtract that 30% from 1. So 1 minus 0.3, which is equal to 0.7, or you can write it as 70%. All right, so that ends the complete discussion on the z-test and the t-test. Thank you.